Alright, I'm going to be going over number 10, homework 1, and I'll be using fictional numbers, random numbers I made up for this. So, there's two valid ways of trying to solve this. You either try to find out when the car and the motorcycle travel the same distance, or when their average velocity is the same. Both are fine, but I'm going to find when the car and the motorcycle travel the same distance. Because if we find that, we can find the position, and we can find the time. It's pretty simple. So, recall this formula from kinematics. We're going to be using some kind of form of this, but if you were to look this up, which is very likely you may have, and saw someone else's work, you may have seen something like this. And you're probably kind of confused. What's T of m, V of m? T of m is time to accelerate to maximum velocity. And V of m is just the maximum velocity. For our problem, we actually will only need to know this for the motorcycle. You'll see why later. Okay, so why for the V of m and t, there's a minus T of m? Well, this, as you know, is a distance equation. So the V of m is the distance traveled when you're going at maximum velocity. But we're not going at maximum velocity the entire time. For a certain period of time that we're accelerating, which we're going to call T of m, we are not going at maximum velocity, so we cannot count that time in here. So that's why we have minus T of m. And T of m, the distance that we traveled, so the distance that we traveled while accelerating is accounted for in this 1/2 AT of m squared. Why that's the case? You have to review kinematics. Okay. So the reason why we have to use this is because the car and the motorcycle are both not accelerating for all of t. Well, at least we can't assume that. They only accelerate for a certain amount of time before the acceleration disappears. So the time they accelerate before they stop accelerating will be T of m in our equations. Okay, great, but how do we find T of m? We know the maximum velocity, but we don't know the time to reach that. Well, we really do, because we can find it, because recall that velocity divided by time is acceleration, or you may see it as v dt equals acceleration, or the derivative of velocity is acceleration. You can see it in a lot of different ways. Not the derivative. Either way, velocity divided by time is acceleration. Maybe it is the derivative. But, so we know what the velocity they can accelerate to is, and we know the acceleration. So we know v max, and we know acceleration. So we can find the time to reach maximum velocity pretty simply. So here's a very, very important realization for this problem. The motorcycle will, for sure, reach maximum velocity before the car reaches the motorcycle. So the motorcycle will reach its top speed before the car catches up to it. That's the most important part. The car might not reach maximum speed, but the motorcycle definitely will. Why? Well, they both start at the same place, and they both start at rest, and the motorcycle accelerates faster than the car. So as long as the motorcycle is still accelerating, the motorcycle will always be going faster, and then the car will never catch it. Only when the motorcycle stops accelerating could the car catch it. So this means that we know that when the car reaches the motorcycle will have to be going at maximum velocity. So that realization lets us make a very powerful assumption that we're going to have so the motorcycle will have a distance traveled when it's accelerating, and it will have a distance traveled when it's going at a constant speed or maximum velocity. That's what this equation right here is. The same as above. However, we cannot make this assumption for the car, because we do not know whether the car will reach its maximum speed before it catches the motorcycle. We have to calculate this. So there's a few ways of figuring out whether the car will reach maximum speed or not. And just to clarify, why do we need to know whether the car will reach maximum speed or not? Because if the car does reach maximum speed before it catches the motorcycle, then we have to include of velocity times by time for when the car is at maximum speed. But if the car isn't at maximum speed when it catches the motorcycle, then only the distance traveled by acceleration matters for the car, which will make our work doable. Much more doable, at least. It's doable both ways. So first we'll figure it out if the car will ever catch the motorcycle by the time it reaches maximum speed. So there's a few ways. This is my favorite method. So the realization is that the way we're going to do this is we're going to find the time it takes the car to reach maximum speed, and then find the distance the car travels in that time, and find the distance the motorcycle travels in that time. If the car goes farther than the motorcycle in that time, then the car must have catched up to the motorcycle before that time, which means before it reached maximum speed. And if the motorcycle went farther, that means the car has not caught the motorcycle before it reached maximum speed, which means there will have to be a speed vector for the car's distance traveled. So we simply just need to find the distance the car goes, but in the time it takes to reach its max speed. To find the time the car takes to reach max speed, just do velocity divided by time, where the velocity is the car's max velocity, the acceleration is the car's acceleration. We find the time, in my case 21 seconds. I just made up these numbers. So now we have the time it takes for the car to reach max speed. We can just find distance using this same old distance formula. In kinematics, you'll know, I call it the distance formula. V naught t is just 0 because the car starts at rest. So we get this distance. So this is how far the car would have gone at the time it reached max speed. So we'll see how far the motorcycle will go in this same time. So recall this formula that we used for the motorcycle to find the distance. We can find this time to reach maximum velocity by the same way we found the time to reach maximum velocity for the car, velocity divided by time, except you plug in the bike's velocity and the bike's acceleration. And it should be less in your car. In my case, it's about 5.5 seconds. So then t of m is 5.5 seconds, and t is just the total time, which is 21 seconds. It's the same as the acceleration for the car, because both of them use the same total time, because they both start at the same time. So then we plug in 21 for t, 5.5 for that, plug in the bike's velocity and the bike's acceleration in this equation. So they'll give you this. If you do all the arithmetic, it'll give you some number. And for all of you, I'd hope at least your distance for your motorcycle traveled should be less than your car goes when the car reaches max velocity. And if that's the case, wonderful. That means for the car, it will never reach its maximum velocity, which means its distance traveled by the time the car catches the motorcycle will be just dependent on the car's acceleration alone. If that is not the case, that by the time the car reaches maximum velocity, it has not caught the motorcycle, then you would have to include the maximum velocity of the car. So you would have to use this kind of equation. But you guys shouldn't have to. I don't think any of you would, because this is a very annoying equation to solve. And I imagine most of you would not have that problem to deal with. But you could still solve this. This is still solvable using algebra. But we'll continue here. So this is the distance that the car goes, and this is the distance that the motorcycle goes. And because we know that the car will not reach maximum velocity before it catches the motorcycle, there is no velocity vector for the car. There's only an acceleration vector. So that makes this so much easier, because we already know every single variable in this equation except total time. We know the acceleration of the car, we know the acceleration of the motorcycle, we know the time it takes the motorcycle to reach max speed, we found it before, and we know the maximum velocity of the motorcycle. So then we plug in all the numbers that we know, which is what I did in these steps. I just plugged in all the numbers that we know. And then I multiply all the coefficients together. And then I distribute. Also, this document will be in the description if you want to read it. So now I have this quadratic equation, if you realize, because it's the power of 2. And there's a first and a 0th power term. So to solve quadratic equations, you set it to 0. And I set this to 0, then I simplified it down to this. And then use the quadratic formula to solve it. In this case, I got about an answer that's about 18, and one other one that's 3. Now, how do you know which answer to use? It's the bigger answer. Why is it the bigger answer? Because remember, we said near the beginning that the motorcycle will, for sure, reach maximum velocity before the car reaches the motorcycle. So if the motorcycle will reach maximum velocity, the time has to be greater than the time it takes the motorcycle to reach maximum velocity. In my case, the time for the motorcycle to reach maximum velocity was about 5.5 seconds. So our answer cannot be smaller than that. So it has to be the bigger number. So once you find the time it takes for the car to go, once you find the time it takes for the car to go how far? Once you find the time it takes for the car and the motorcycle to match up, finding position is super simple. To find the position, you simply just plug in the time on either side, and whatever you're from here. Or here. You simply just plug in time on either side, and that's it. Because once you have time, finding the position is super simple. So, hope this helps.